Okay, in the last lecture, we went over section 3.5, and in 3.5, we kind of had a change in perspective on what the derivative is, and this allowed us to take derivatives of equations. So, which is sort of what we've been doing all along, as I noted. So if I give you a function of x, you can define an equation associated to that function, just set y equal to f of x. And then you can look at the x and y that satisfy that equation. You can plot this. Um, you can plot the curve associated to this equation, and then you can find the rate at which y changes with respect to x by differentiating. And we saw that you do this by just applying the derivative operator to both sides of the equation. And then the idea is, well, what's stopping us from differentiating just any equation? And in fact, there's nothing. So I can give you any equation in the variables x and y, or basically any equation in variables x and y, and you can find out the rate at which y changes with respect to x, even if you can't write y as a function of x. So for example, if you plot the curve, maybe it doesn't satisfy the vertical line test. So you can't write y explicitly as a function of x, but y isn't implicitly defined in terms of x. So it still makes sense to talk about the rate at which y changes with respect to x. So if I give you an equation, you can plug in a value of x, and you get a certain y value when you solve for it. And then if you plug maybe a different value of x in and solve for y, you'll get a different value of y. So y is changing with respect to x. So even if y can't be written as a function of x, it still makes sense to talk about y changing with respect to x. And that's essentially what the derivative is. How does one quantity instantaneously change with respect to another quantity? We also saw that when I give you an equation and you plot it, it still makes sense to talk about tangent lines, and that's exactly what the derivative is about. The derivative, remember, gives you the slope of the tangent line. So, with just a slight change in perspective, we can really generalize this process of differentiating from just differentiating functions to actually differentiating equations more generally, which might not correspond to functions. Now, in this lecture, we're going to go over 3.6, and aside from and what we're going to see is that actually this idea of implicit differentiation is going to be even more useful than beyond just finding say tangent lines to curves. It's actually going to allow us to define sorry, it's going to allow us to differentiate inverse functions. So remember, if I give you an injective function, you can define an inverse, and it's defined in terms of an equation. So that's going to allow us to actually find derivatives of inverse functions by differentiating that defining equation. All right, so let me share my screen. So this is going to be, we're somewhere in section 3.6. So 3.6, and this is on derivatives of logarithms, which remember, the logarithm is the inverse of the exponential function, and that we know how to differentiate. So logarithmic and inverse trig functions. So we're going to look at just differentiating inverse trig or inverse functions more generally. So just recall. So let me get the convention right. I just want to make sure. All right. So if let's say f from D to E, and again, always D will be a subset of the reals, and so won't E. I should note that a lot of this stuff that we're doing generalizes to higher dimensional spaces. But we're just dealing with the real numbers. So if this is injective, then it's an injective function. We can define its inverse. Oops, that's not how you spell that. So its inverse function, and it's denoted as f to the -1. And now this is a function from e to d, and it's as follows. So remember, the inverse is defined as follows. It's if I give you an input, so it's defined by this equation. So actually, let me say, so let's say, oops. So for y in here, or y in E, which is the domain of F inverse of y sends F inverse sends y to x if and only if F sends x to y. So in other words, to figure out what the inverse function does to a given input, call the input, so the input is y, call the output x, and x, whatever x is, it has to satisfy this equation. So this is like an implicit relationship that we can differentiate. Not always, not every inverse function is differentiable, but all the inverse functions we're looking at are going to be differentiable. So let's apply this to a specific example to the log function. So let's recall this. Let's say, how do we want to say this? So f is a function from R to the positive numbers given by f of x is equal to b to the x. I might be doing this backwards a bit. Let's see. Yeah, maybe I don't want to do it this way. Yeah. Okay, but the idea is as follows. Let's actually just say this. Recall. Oops, I already wrote recall. Let's just recall this, that b to the x and log base b of x are inverses of each other in the above sense, in this above sense right here. So in other words, what that means, in other words, if you say y is equal to log base b of x, that's the case if and only if b to the y is equal to x. So in other words, like if you want to figure out, I know I wrote, I kind of got x and y reversed compared to the definition, but that's okay. Just imagine everything reversed a little bit. But in other words, what this says is to figure out what the log function does to a given input x, call that output y, and whatever the y that satisfies this equation has to also simultaneously satisfy this. So like this is an equation we can solve, and it will allow us to figure out what the log of a given input is. Or in other words, in this specific example, this says that the logarithm, log base x, sorry, the log base b of x is that number such that when you raise b to it, you get x back. And that's just the cancellation property. So I mean, you can even combine these as saying the following, that log base b of x is equal to x, and that log base b of b to the x is equal to x. All right, so here's the claim. So the claim is that when you differentiate the logarithm, that you get 1 over x ln natural log of b. So it's like x times that. All right, so here's the proof. and it's going to use implicit differentiation. So what we're going to say is let y equal to log base b of x, then by definition of the inverse, or let's say because log base b is the inverse of the exponential in the above sense, we know then that when you take b to the y, it's going to be equal to x. Now let's implicitly differentiate this. So we're going to implicitly differentiate this. So remember, it's just an equation. We can definitely differentiate this. And we can do this. We can do this because the exponential function is differentiable. Remember, I had that one peculiar property that if you know it's differential, if you know the exponential function is differentiable at x equals 0, then it's actually differentiable everywhere. So it's it's a very strong property about differentiability of the exponential function. So we're going to implicitly differentiate that. And so what you get when you do that is, well, we have b to the y. So we have like a composition here. All right, let me write the equation down here and then I'll differentiate it. So first of all, the right hand's, let me just write it like this. So we're going to differentiate this equation. All right, so the right hand side is pretty easy. If you take the derivative of x with respect to x, you just get one. That's just the power rule. Now the left hand side, we have to be a little careful because we have like b to the y, and y is actually implicit. It's defined as this. So y is actually a function of x, so it's definitely changing with respect to x. So we need to use the chain rule. We have like a composition of two functions, y with the exponential function. So according to, if you remember back when we talked about the derivative of the exponential, this derivative right here is going to be equal to b to the y. So we're taking like the derivative of the outside function. So the derivative of the outside function is just the exponential function itself times, let's put this in parentheses, ln of b. So I took this is the derivative of this part right here is the derivative of the outside function evaluated at y. So derivative of outside function, and then we're evaluating it at inside function, and our inside function is y. And now, but the chain rule says so we took the derivative of the outside function, and the chain rule says we need to multiply by the derivative of the inside function, and that's just dy dx. So now, this right here is just the right hand side. I'm sorry, the left hand side. This thing I wrote here. So let me carry this down now. And so on the left hand side, we have b to the y ln of b times dy dx. So that's differentiating the left hand side using the chain rule. And the right hand side, remember, it's just this derivative right here is just going to be 1. All right, so now this is what we want. This is what we want. We want the derivative of, because this is going to be the derivative of the log function. So let's solve for that. So dy dx is going to be 1 over b to the y times ln of b. All right, now let's plug in y. What was y again? Remember, it was the log base b of x. So if you plug that in, this equation right here becomes the derivative of log base b of x is equal to 1 over b to the y, but y is equal to log base b of x, log base b of x times log of b. And then we can simplify this a little bit, we can use our cancellation property for inverse functions. Oh, I gotta pull this down now. Let's see. Ran out of room. Yeah, so we can just use the cancellation property. Is this working right here? It's picking up my audio. Doesn't seem like it's reading. Let's see if my microphone works. I guess it's working. All right. Hopefully it's working. So now we're gonna use the cancellation property, and this is because we can do that because the log and the exponential are inverses of each other. So the derivative of log base b of x is gonna just be 1 over x times ln of b, and that's exactly what we claimed above. This is going to be so the derivative of log base b of x is equal to 1 over x times ln of b. All right, so we're mostly not concerned with b just this base right here being any number. Let me actually just put this little box because we're done with the proof. We're usually concerned with using that natural exponential function, using the Euler constant. So we get a special case, and the formula reduces even more. It's very nice. So the special case is that when b is equal to e, and this is that Euler constant, and we're actually going to be able to finally define the Euler constant, which is unusual that and what we need is all these ideas we develop. So it's kind of unusual that you need to develop a whole branch of mathematics to define this number. So this is Euler's constant, remember? So when b is equal to e, this formula reduces quite a lot. So we get derivative of log base e of x is equal to 1 over x times ln of e. And that reduces even more because we have special notation for this, and then ln of e is just 1, right? So this will be log, the derivative of ln x is just simply 1 over x, and that's nice. So that's the derivative of the inverse function of the exponential. So now let's look at some examples on how to use this formula, and note that we had to use this idea of implicit differentiation. So here's like a first application. So aside from being able to find, equations of tangent lines and finding rates of change, the implicit differentiation can be used to find further derivatives of functions, in particular derivatives of inverse functions. All right, so now that we have this formula, let's use it to compute some derivatives. So we want to differentiate the following function. Y is equal to ln of x cubed plus x. All right, so we know how to take the derivative of ln x, 1 over x, but we don't just have ln x here. We have ln of x cubed plus x, so we have to use chain rule. We have a composition of functions, right? All right, so the derivative of y dy dx is going to be the derivative of ln of x cubed plus x. And so this piece right here is our inside function, and the ln is our outside function. The outside piece. And the chain rule, so this is going to go to, this step is going to be by the chain rule, says that you take the derivative of the outside function, which is 1 over x, but then you evaluate it at the inside function. So it's going to be 1 over x cubed plus x, and then times the derivative of the inside function, which is going to be 3x squared plus 1. And then that will be 3x squared plus 1. You can multiply these, the numerator and denominator, and get this. All right, so let's look at another example. So this is example 2. And we want to find, find the derivative of natural log of sine x. So again, we need to use chain rule. So we have the derivative, let's compute this derivative. So we have derivative ln of sine x. So this piece is our inside function, and the natural log is our outside function, the outside piece. So the chain rule says take the derivative of the outside function, which is pretty simple, it's just 1 over x, and evaluate it, compose it, that is, compose it with the inside function. It's 1 over sine x. And then what you're going to do is you're going to multiply by the derivative of the inside, which is cosine. And then what you get is cosine x over sine x, and that's actually equal to cotangent, remember. That's equal to cotangent of x. All right, let's look at another example. So these aren't that bad. These, they're not terrible. If you notice there's a pattern, it's if you have ln of some function, so maybe I'll just write it like this. And this is, maybe I'll just make this as an observation. So here's an observation. And it just is literally what we've been doing. It's just a simple application of the chain rule. If you want to take the derivative of ln of, say, g of x, where you're going to assume that this is differentiable, right? Otherwise, it is not going to really make sense to take this derivative. By the chain rule, so by chain rule, the derivative is just going to be g prime of x over g of x. So pretty easy derivative to compute. And it's just a simple application of the chain rule to prove this observation. So when you have simple propositions or simple statements like this that are like literally just one line proofs, you never really even prove them, you just state it as an observation. So that doesn't really require proof because it's almost so obvious. Of course, if it's not obvious, feel free to ask, why is this true? Why is this observation true? And I'd be more than glad to answer that, because sometimes things are, there's like a psychological aspect to learning mathematics. Like some things are obvious to others, and some things are obvious to one person, but maybe not to another person. So, all right, let's look at another example. So this is example 3. So we want to differentiate f of x is equal to square root of ln of x. All right, so now, so we want f prime, and that's going to be the derivative of, I'm going to write this as ln of x to the 1/2. So now the ln is our inner function, the inner piece, and the square root, this 1/2 power, is the outside piece, the outside function. So according to the chain rule, I take the derivative of the outside function. So I'm taking basically the derivative of x to the 1/2. And by the power rule, that is, you bring the power down, and then you reduce the power by 1. So you subtract 1 from 1/2, you get negative 1/2. But the chain rule says now you got to compose that with the inner function. That is, you got to evaluate it at the inner function. And now you multiply by the derivative of the inner function, which is just simply 1 over x. And then we can rewrite this as follows: 1 over 2, say x, times square root of ln of x. All right, let's see. So let's look at one more example maybe, and then move on to some other problems. I'm going to skip over an example or two. So I stopped at three. I'm going to probably go over just five. So I'm going to skip four and six. So definitely read through those yourself. And if you have questions, just let me know. All right, so this is going to be example four. All right, so we want to find the derivative of ln of x plus 1 over square root of x minus 2. At first, like, okay, so we have these pieces. This is our inside piece, and it's a fraction, and then our natural log is our outside. And yeah, this could be pretty horrible at first, right? Because if we want to just directly apply the chain rule, we would have to take we would have to take the derivative of the outside function, which is 1 over x, and evaluate it at the inside function. So that part's not bad, but then we would have to take the derivative of the inside function, and that would involve quotient rule. Now you can do it that way, that's perfectly legitimate. But if you remember your laws of logarithms, you can actually simplify this. So if you remember your laws of logarithms, and then the fact that the derivative is linear, it's a linear operator, you can simplify this derivative quite a bit. So let's see how to do that. Um, of course, you can do it the other way with the quotient rule. That works fine too. If you don't remember these laws of logarithms, but I would definitely remember them because they're gonna come up a lot when we do um, logarithmic differentiation. All right, so now what I'm gonna do is before I take this derivative, I notice I have a fraction here, so I am going to split the fraction up. It's going to be the difference of the logs, right? So it's going to be ln of x plus 1 minus ln of square root of x minus 2. And then I'm going to use another log rule. Let me bring this down some more. Um, well, first of all, so I have this negative, so I can just distribute the derivative over it. So I get the derivative of ln of x plus 1 minus the derivative of ln of square root of x minus 2, but I'm going to write this as x minus 2 to the 1/2. And now I'm going to use another log rule. It says when you take the logarithm of something to a power, so this is our something to this power, the power becomes the coefficient. Now, I'm going to now just take this derivative, and we know how to do that. It's going to be, remember this observation I wrote up here? So we're going to use this observation. We just to differentiate the logarithm of some function, say g of x, it's just the derivative of g of x over g of x. So this is going to be 1, the derivative of x plus 1 is 1 over x plus 1. And then minus 1/2 derivative of ln of x minus 2. And then that's x plus 1. And now I'll take this derivative. So it's 1/2 of 1 over, so 1/2 times 1 over 1, 1/2 times 1 over x minus 2. And that's it. You can just leave it like that if you want. You can combine these fractions, but you can just leave it like that. So this is a lot easier than having to use the product rule or quotient rule. Of course, this is a completely legitimate way, but a little more complicated. I need to pause for a moment. Okay, so the next thing we're gonna look at is actually this process of logarithmic differentiation. I didn't realize it was actually in this section that we learn that. So let me share my screen again. So let's look at an example to sort of motivate this process of logarithmic differentiation. So it's going to be a trick. So let's see. So this is example 7. This is on logarithmic differentiation. We're still in the same section though. So here's what we want to do. Here's the task. We want to differentiate y is equal to, sorry, y is equal to x to the 3/4 times square root of x squared plus 1 divided by 3x plus 2 to the fifth power. Now, if we just differentiated this, what would let's just not go through the actual steps, but just imagine what would it would involve. First of all, we have this quotient, right? So first we would have to do quotient rule if we wanted to differentiate this. And that, remember, quotient rule involves differentiating the numerator and the denominator separately and then kind of putting these pieces together. Sorry, so far we need quotient rule. And then we would need to take the derivative of the numerator. Well, there, right here, you can see we have a product. So we have a product of x to the 3/4 times square root of x squared plus 1. So now, not only would we have to do quotient rule, but we have to do product rule. But what notice in this product, there's a square root of x squared plus 1, and that would require chain rule. And then, of course, the bottom would require chain rule as well. So this is getting, you can imagine this is becoming a very complex problem. However, here's this trick. Here's a trick we're going to use. We're going to just take the natural log, uh, take natural log of both sides. Both sides. See what happens. What do we get? So let's take the natural log. So I claim that it's going to be easier to first take the natural log of both sides and then differentiate, and then the derivative of y is going to pop out naturally, and we'll be able to solve for it very easily. So if you take the natural log of both sides, you get ln of y is equal to ln of 3/4 times square root of x squared plus 1 divided by 3x plus 2 to the fifth. And when you take a natural log, it has a way of like sort of linearizing an expression. So we can write the right hand side using the various laws of logarithms. We have this quotient and this product. And so when you go through the whole process of using the laws of logarithms to expand the right hand side, what you're going to end up with is 3/4 log of x plus 1/2 log ln, natural log, of x squared plus 1 minus 5 times natural log of 3x plus 2. If you don't see that, pause the video and try to see why this thing right here is equal to this right hand side right here. And now if we take the derivative of this, you can see this is actually a lot easier, right? This is going to be a lot easier. And because we know how to compute the derivative of ln x and ln x squared plus 1 and ln of 3x plus 2, they're pretty simple derivatives. So now we're going to implicitly differentiate sides. And so you can see in the original problem, y is explicitly a function of x, but somehow it's easy, and so you can compute its derivative. You can definitely compute its derivative. But somehow it's actually easier to convert it to like an implicit relationship between x and y by taking the natural log of both sides and then differentiating and then kind of like undoing everything. So when we implicitly differentiate both sides, so that we're going to take the derivative of ln y, remember by that observation, it's going to be y prime over y. And now we just differentiate each piece on the right-hand side. It's going to be 3/4 times 1 over x plus 1/2 times 2x over x squared plus 1 minus 5 times 3 over 3x plus 2. And then what we can do now is, so as I said, y prime kind of just, which is what we're trying to find, just pops out naturally. Now you might complain or protest, well, look at this, there's this y here, and so this won't show y prime explicitly as a function of x, but we can substitute back in and get that. Because remember, this is y itself right here. So we're going to multiply both sides by y. So what we get is y prime is equal to y times 3 over 4x plus x over x squared plus 1 minus 15 over 3x plus 2. And then we'll just substitute in for y. So remember, y is going to be x to the 3/4 square root of x squared plus 1 over 3x plus 2 over 5, and then times the rest, this thing in the parentheses. So 3 over 4x plus x over x squared plus 1 minus 15 over 3x plus 2. And if you might think to yourself, well, that's kind of complicated. Well, it's much better than the alternative, which was to use the quotient rule, then use the product rule, and then use chain rule multiple times. So this is definitely much better than the alternative. All right, so let's look at let's look at another example where actually you can't avoid this process of logarithmic differentiation. I don't think there's a way of doing this without using logarithmic differentiation. Let's see, so we want to differentiate y is equal to square root of x raised to the, oh, sorry, not square root of x. It's going to be x raised to the square root of x power. So I don't think any of the rules we've learned will allow us to compute this derivative. I think you have to use logarithmic differentiation. So what does that involve? Well, that involves taking the natural log of both sides. Okay. And now we have x to some power. In fact, the power is square root of x. But by using our log rule, we can bring that square root of x down as a coefficient. And now we've reduced this really awful looking problem to just product rule, right? We have a product of two functions, and we know how to compute this derivative, and we know how to compute this derivative. So if we implicitly differentiate both sides of this equation, we're going to get y prime for y is equal to, by the product rule, it's going to be the derivative of the first function, which is 1/2 x to the -1/2, times the second function, plus the first function times the derivative of the second function, which is 1 over x. And so when you do that, now we have, again, y prime, which is what we're interested in, pops out naturally from this implicit differentiation. So now we have y prime is equal to y times, let's see, can we simplify this a bit? So it's ln x over 2 root x, and then this becomes, I guess, when you simplify this, it becomes x to the 1/2 minus 1, so it's going to be x to the -1/2, so it's x to the square root of x, 1 over square root of x. And then remember, y is equal to x square root of x, and then I guess you can combine these fractions to get ln of x plus 2 over 2 root x. All right, let's see. So now let's I'm actually gonna skip this. There is a little section here. I'm not actually skip it. I thought I was gonna go over it, but I'm gonna skip it for the sake of time. there's a subsection on the number e as a limit. So I encourage you to read this. It's not that difficult. It's not even a whole page, but it shows you how you can define that Euler constant e as a limit of a function. And so, in other words, in order to define this number, you need the ideas of calculus. You need a whole branch of mathematics to define a number, which is kind of odd if you think about it. And instead, we're going to skip to looking at derivatives of inverse functions. So we looked at derivatives of logs, which are the derivative, which is the derivative of the inverse of exponential function. And now we're going to look at derivatives of other inverse functions. All right, so let's see. So let's call this maybe like just a new, this is still the same section, but it's like a subsection, derivatives of inverse trig functions. Oops. All right, so derivatives of inverse trig functions. So remember, let's recall the definition of the inverse sine function. So recall that y is equal to sine inverse of x if and only if sine of y is equal to x. This is just what it means to be the inverse. This is what it means. This equation is just what it means for this function to be the inverse of the sine function. So this equation holds if and only if this equation holds where we're considering y between negative pi over 2 and pi over 2. Remember, the sine function itself does not have an inverse because it's periodic, remember. But if you restrict the domain, you will get to this. If you restrict the domain of the sine function to this interval, you will get an injective function. So now we're going to differentiate this, implicitly differentiate this. So we're basically kind of doing this. Oops, that's not how you spell that. Implicitly differentiate this, which is exactly what we did with the log function. So when you do that, so let's carry this down right here. So we're taking the derivative with respect to x of sine of y. So we're taking the derivative of both sides of this equation. And that's going to imply, so first of all, this derivative on the right-hand side is easy. That's just going to be 1. This requires chain rule. So to do this, we need to take the derivative of the outside function, so derivative of sine, which is cosine, and then evaluate it at the inside function, which is y. And then multiply that whole thing, let's put that in parentheses, I guess, times the derivative of the inside function, which is dy dx. And this is what we're interested in right here. Because remember, y is equal to the inverse function. So this will give us the derivative of the inverse function. And then the other side, the right-hand side is 1. And so we can solve for dy dx. That's going to be 1 over cosine of 1 over cosine y. So for at this point, we hold on, let me pull this down some more. So at this point, it's kind of not exactly, so let me actually write this as, so what is y? Remember the derivative dy dx is going to be the same thing as the derivative of sine inverse of x. Whoops, it's kind of messy. And so far what we've shown is that it's equal to 1 over cosine of y, but that's not so good. And even if we plug in y, right here, we would have cosine of, we'd have, if we plugged in for y, we'd have cosine of sine inverse of x, and that's kind of messy. But if we recall by the Pythagorean theorem, we know that cosine squared y plus sine squared y is equal to 1. So that implies that cosine squared y is equal to, or well, if you just do the whole simplification and solve for cosine y, it's going to imply that cosine y is equal to 1, oops, square root of 1 minus sine squared of y. But this is nice because, oops, um, sine of y is x. So now we can like re-express everything in terms of x. We can completely eliminate y on the right hand side. So this is going to be equal to 1 minus x squared. So we can completely eliminate this y right here and just express the whole equation in terms of x, which is good. So we want to eliminate that variable y. So what that implies then is that this implies, so kind of bring this down here, this implies that the derivative of sine inverse of x is equal to 1 over square root of 1 minus x squared. So maybe put a little box here. And you can basically do the same exact, you can do the exact same calculations to prove some the other formulas. I'm not going to go through them. And in fact, the book doesn't even go through them, it just leaves them as an exercise for the reader. But I'll show you them right now. And they're not hard to prove. You just go through the exact same calculations. Maybe I'll even make that as a bonus in a quiz. So here are all of the derivatives. So notice in this case right here, you get a negative with the cosine inverse. And that makes sense because you're going to take a derivative at some point when you use that defining equation for inverse functions, you're going to take the derivative of cosine, and the derivative of cosine is negative sine. So a negative should pop up, but the formula basically looks the same as this one. It's just you have this derivative, this negative, and that comes from the fact that when you take the derivative of cosine, it's negative sine. This one just kind of, I mean, you can't really argue by analogy. You just got to go through the calculation. But this one, but again, it's not that hard to get this one. These ones are just as easy, not that hard, but I doubt these are going to come up. I don't think they'll come up at all, really. Um, anyways, so let's look at some examples. All right, so let's see, what do we have? All right, so example 9. So this is example 9. So we have, this is two parts. We have y is equal to 1 over sine inverse of x. So we want to differentiate this, and then part B is we want to differentiate f of x is equal to x times, it says arc tan in the book, but I don't like using the arctan notation. So I'll just do tan inverse of square root of x. So let's do a first. So I would write a as so I'd write this as a fraction. I want to write it as something to a negative power. So it's going to be sine inverse of x all to the negative. Now note, this negative right here is not an exponent. It's just to denote the inverse function. This is an exponent. So don't say like, oh, I can just like distribute this exponent over to this one, and then you cancel them out somehow. That would not be right at all. That's not right. This, let's say this not an exponent. this right here is an exponent. So don't get the notations confused. And that's another like difficult aspect of mathematics. It's like mathematics itself isn't hard. It's just like getting used to notation, conventions, terminology. This like new language. So this right here is not an exponent. It's just notation to denote the inverse sine function. This is an exponent. So don't think you can distribute this exponent to this one and can't and then multiply the exponents because the other one is not an exponent. Anyways, let's differentiate this. So now it's now that it's of this form, it should be fairly clear how to differentiate this. We need um to use the chain rule. So we have sine inverse of x is our inside function. And in fact, all right, let me rewrite this over here. So I'm just writing the same thing down. So this is going to be our inside piece, our inside function, the inverse sine function. And the exponent that's -1 is our outside piece, our outside function. So according to the chain rule, you take the derivative of the outside function to the -1. So it'll be, you throw a -1 in the front, and then times, it's going to be something to the -2, but now you got to evaluate it at the inside function. You have to compose it with the inside function. So it's going to be sine inverse of x. And then that's times the derivative of the inside function. And this one we just found. We found that when you take the derivative of the inside function, sine inverse of x, it's going to be 1 over square root of 1, square root of 1 minus x squared. And then I guess you can simplify that a little bit to get -1 over, let's say, it's kind of horrible looking, sine inverse of x, oops, squared times square root of 1 minus x squared. All right, so that's part A. Now let's do part B. So B is f of x, recall, is f of x is equal to x tan inverse of square root of x. So we have first of all, we have a product here, and then we don't just have tan x inverse of x, we have tan inverse of square root of x. So we need chain rule for this piece, and then we have a product rule here. So we got to kind of combine all these things together. So the product rule says you take the derivative of the first function, which is x, and that becomes 1, times the second function. So it's 1 times tan inverse of square root of x, plus the first function, and now don't do anything to the first function, but take the derivative of the second function. So it's tan inverse of, oops, square root of x. All right. Now we'll just deal with this derivative right here kind of separately. Always break this up into pieces. Don't try to do all these derivatives at once in your head. It's not more than likely not gonna work out on your first run. This is supposed to be prime. So f prime of x is equal to tan inverse of square root of x plus x. And now this derivative right here, so maybe I'll just write this on the side so you note, so you don't have to constantly look down at your paper. The derivative of tan inverse of x is 1 over 1 plus x squared. All right, so now what's this derivative right here? Well, that's chain rule. So I have my outside function is tan inverse, and my inside function is square root of x. So according to the chain rule, I take the derivative, so this is times the derivative of the outside function, which is this right here, so it's going to be 1 over 1 plus x squared, but I have to evaluate it at the inside function, square root of x. So it's going to be 1 over 1 plus square root of x squared, and then I multiply by the derivative of the inside function, the square root of x right here. So that will be 1 over x to the negative 1/2. All right. And then I guess when you simplify this, let's see, what do you get? You get so this the second term here is going to be oh, okay, so you have an x here, and then you have x to the negative 1/2. So in the numerator, we're going to get square root of x over 2 times this denominator right here. It will be 1, so it's 1 plus square root of x squared, which would be x. All right, let's see. All right, I think I'm just gonna leave it at that. There's example 10 with secant inverse. I guess maybe it would be a good idea to go through that. Um, I doubt secant function will come up. I don't want to make any promises, but this is a relatively straightforward example, so I'll allow you to go through that on your own. So that's all we have for this lecture.